Hello everyone. In today's session, we'll understand the experiment verification of sampling theorem. So myself Shreeshayana, Assistant Professor, Department of EEE, ATME College of Engineering, Mysuru. So the sampling theorem is attributed to the Nyquist, Shannon, Kottnikov and Whittaker, who actually were instrumental in coming up with this theorem. They proposed to calculate the sampling frequency that is required, which is used in analog to digital converter. Now, before proceeding further, let us understand what is sampling. Sampling is a process of converting a continuous time signal, that is, here you can actually observe it is represented as x of t, into discrete time signal x of n. Now, why is this actually came up or proposed for? Now let's say we have a case of an image data. Let's say, for example, an electrocardiogram data which is taken in a hospital. Now suppose if I want to store this data, if a doctor wants to store this in a HIS, that is Hospital Information System, or a Radiology Information System, he cannot store the image data as a continuous signal or a continuous data. He has to store it in discrete data form in a server or in a hard disk or in a floppy drive or a pen drive, wherever he wishes for. And that is the very reason why sampling comes into picture, which helps in the conversion of data from analog to digital form. But it is also important that once the data which is stored in digital form is retrieved back to its original signal. Hence, further, it was proposed in sampling theorem that to get back the original signal, the theorem stated that a band limited signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency. You have to underline the marquee sentence here, twice the maximum frequency. This is the Nyquist frequency sampling rate. So this is what was proposed by the Nyquist. So here in this experiment, we'll be coming across three different cases. That is, one is for undersampling of frequency. What happens if I sample a frequency lesser than the sampling frequency? Oversampling condition will come across, and the proposed Nyquist sampling condition. So here let us represent the signal as g of t and the sampling frequency as fm. To recover the signal g of t exactly from its sample, it has to be sampled at a rate twice the fm. Like I said, fm is your sampling frequency. So the minimum required sampling rate is fs equal to 2fm, and this is called as your Nyquist rate. Now further, here we have proposed a simple algorithm. Like I said, we'll be working out for three different conditions. So here we'll be programming using Matlab software. You can also use Octave or any other open source software. Here we'll be writing the input frequency fm. So it can be any desired frequency by the user. So you can generate the continuous signal. It can be either a cosine or a sine wave. Once this is done, you have to generate discrete signals, that is for your undersampling, Nyquist and oversampling conditions. So here we have gone for three different cases. Here you can actually check out for undersampling condition. We have actually chosen fs1 is less than twice fm. Fm is your sampling frequency, and you can observe we have gone for fs1 as against fs. The reason is once you have used a keyword fs, you cannot again use it further in the program, and that is the reason why you have used another keyword fs1. So for the rate, even will become fs1 because 1 by. So here it is represented sampling as twice the sample. So fs2 is equal to twice the sampling frequency, and lastly for oversampling it is greater than sampling frequency. Next we'll understand the program functioning. Now let us understand the program execution. So here in the program you can actually check out we have used certain commands for our program functioning easiness. As soon as we commence the program typing, you can actually check out we have used two commands here. One is CLC and clear all. CLC actually clears the command window in your Matlab or Octave or any open source softwares where the code can actually be utilized or the program command can actually be utilized. Similarly, clear all helps in removing the items from workspace, any matrices which is already pre-available. So once this is done, we are actually generating a continuous analog signal which will later on be discretized or will be actually digitalizing it for undersampling and oversampling condition, and along with that Nyquist sampling condition. So to generate your continuous sign using FM here your desired frequency, so we are randomly taking 0.02. You can take any frequency as desired, and then you can actually check out the program functioning in the Matlab software. So here with respect to your time domain, that is the scale, we are taking from -100 to 100. It is not mandatory that you take the same time length. You can take it for anything, or you can even start it from 0 as well. So next, if you want to plot this entire thing, you will be using plot t of x. T is your time length and x is your signal, that is sine 2 pi ft. So subplot is actually helping in creating a grid, that is creates axis in tiled positions. So you can have a number of subplots within this, and for my first subplot I'm using 2, 2, 1. Similarly, if you want adjacent to it the next subplot, you can have 2, 2, 2. However, in this particular length of program I'm not requiring it. In further sections I'll be using subplot again. So in addition to visualization purpose, if you want the labeling, you can use x label, that is time in seconds. This is with respect to t, and y label x of t. This is your continuous time signal sine. So once this is done, now I'll actually be going for my next case. Here I'll be simulating my condition for undersampling case. So that is fs1 is less than twice desired frequency. So fs1 I'm taking as it is. I'm not changing it right now. If you want, you can actually reduce it, and you can actually check out or observe in the graph. And once this is done, my time length here, you can actually observe I'm not going for t, rather I'm going for n. So the time index here is from -2 to 2. It is not mandatory you go for this length itself. You can go for any length, like I said before. Once this is done, I go for my next, that is my x1. Here either you can go for sine or cos. There's a small mistake. This should be sine, since we have gone for sine previously. So this is sine 2 pi fm n by fs1. How it is n by fs1? This is 2 pi ft. So t is equal to 1 by f. Here n represent my time index, so I'm using this, and fs1 we have already taken the desired frequency. So once this is done, you'll be obtaining the plot like I showed in the previous slide. Subplot 2, 2, 1. Now this becomes 2, 2, 2. So you'll be getting your second graph in the same grid. Next, stem n, x1. Now what is this for? This helps in plotting my discrete sequence data. If you want your continuous data to be represented in discrete form, stem is the command which you'll be using here for. Here n is your time index and x1 is your signal. Now after this, hold on, we'll be using the command which helps in retaining my current graph in figure. So once this is done, so hold on helps the plot to retain, and then you'll be using that again in subplot. So plot n, x1 is your total, and all this works in coherence. That is, you are actually plotting, but your actual program part is only these 3 commands. So if you want to visualize this entire plot, you will be going for all these commands. So once this is done, so you will be getting your undersampling case. Next, Nyquist case we have already come across. It should be twice the desired frequency, or here you can actually check out I have gone for 0.04 as against 0.02, that is twice. Next, time index have increased -4 to 4. This remains same, but you have to observe here I have not used the same commands which I have used previously. X1 I have not used, I have gone for X2. So wherever you are actually checking out, that representation which has already been used will not be used. So you have to be very careful with respect to that. N1 is your time length. In previous program we are actually given N. Here it becomes X2. So again, this is not cos. Kindly rectify. It is sine. Since we have gone for sine, can I use cos? Yes, I can go for cos as well. Either one of the cases, it would be more ideal. Next, the remaining section remains as it is, like what we had shown previously. So we'll be checking out the Nyquist plot condition as well. And lastly, your oversampling condition. So I've increased the sampling desired frequency. So you can actually check out the time length I've increased, and here I've given 0.5, which is definitely greater. So rest all commands, as against X2 I've used X3, and can also observe in stem as against N1 I've gone for N2 and X3. So rest all section remains same, that is hold on, subplot, plot, and labeling and titling of your entire program. So this is your program with respect to sampling theorem. Next, we'll see how this program executes in Matlab. Okay, now let us observe the execution of this program in Matlab. I've already opened Matlab Software. In your case, you have to just double click on the Matlab Software, and as soon as the Matlab Software is open, you can actually check out the command window pops up like this. So there you have to go to File, New, and M file. So M file here is your matrix file. Either you can go like this, or you can also go for shortcut file like this. Already copied the program which I had explained before. So in your case, you have to just type it. It will take a few minutes, and wherever you are using comments, always see that you use percentage symbol, else the statement also becomes part of the program and it becomes syntax error. So always see that you use this symbol. Once this is done, there are a lot of tool icons that is available here in the bar. So you'll actually be interested in only running the program and observing the output. So I'll just first save the file, which is important. So I'll save it. So I'll save it in desktop. You can save it in any folder that you want. So I'll save it as sampling theorem. So sampling theorem, I'll save it. Once this is done, I'll execute this. So let's run this, and you can actually check out the output, and this is your continuous time signal. And here you can actually observe the undersampling case, and you can actually observe if I try to rejoin this entire signal, you're not getting back the original signal. And here this represents your oversampling condition, that is fs greater than 2 times fm. And here also, if I try to join back my signals which is sampled, you're not getting your original signal. And finally, your Nyquist sampling, that is fs equal to 2 times fn. So according to the theorem, so we have shown that if you rejoin this back, you are getting back your original signal, and this is what you desired for. And this is your experiment with respect to verification of sampling, and I'm sure that you're convinced with respect to this experiment. Thank you.